Welcome to the fastest way to learn data structures and algorithms, with this premium revision material. Today, we are mastering LeetCode 45, the Jump Game 2 challenge. This problem is a classic at top-tier companies like Amazon, Google, and Microsoft. It is part of the top interview 150 list and tests your ability to think greedily. Let us look at the goal. Our mission is to find the minimum number of jumps required to reach the last index of an array. Each element in the array, nums of I, represents your maximum jump length from that position. You start at index 0, and you are guaranteed to reach the end. The challenge is not just reaching the finish line, but doing it with the fewest possible steps. Think of this like planning a flight route. Imagine each index is a city with its own airport. The value at that city, nums of I, is the flight range of the planes available there. To minimize stopovers, you do not just jump as far as possible every time. Instead, you look ahead to see which city in your current range has the plane with the best future reach. You only take a jump when you absolutely have to, which is when you reach the edge of your current range. This way, you always maximize your horizon. Our strategy follows a golden rule: look ahead to the farthest reachable point. We use a greedy approach with a jump end boundary. We scan the array and always track the farthest index we could possibly reach from any city visited so far. We only increment our jump count when our current city pointer reaches the boundary of our current jump range. At that moment, we take a jump and expand our horizon to the farthest point found. Now, let us dive into the dry run. This is the most important part. Look at our array on the screen. The values are 2, 3, 1, 1, and 4. Notice the variable tracker box below. It tracks our jumps, our current end boundary, and the farthest reach found. We start at index 0. Currently, our pointer I is at index 0. The value is 2. This means from index 0, we can reach up to index 2. Our farthest reach updates to 2 in the tracker. Since we are at our starting point, which is also our initial current end, we must jump. Our jumps count increases to 1, and our current end moves to index 2. We have now established our first horizon. Next, we move to index 1. The value here is 3. From index 1, we can reach index 1 plus 3, which is index 4. Since index 4 is farther than our current farthest of 2, we update the farthest tracker to 4. Look at the pink highlight showing this new potential reach. Notice that we do not jump yet because we have not reached the end of our first horizon at index 2. Moving to index 2. The value is 1. From here, we can reach index 2 plus 1, which is index 3. Since index 3 is not better than our current farthest of 4, our farthest remains 4. Now, look closely. We have reached our current end boundary at index 2. This is the moment we must take our second jump. Our jumps count increases to 2, and our current end expands to the farthest reach we found, which is index 4. Next, we move to index 3. The value is 1. From here, we can reach index 4. Our farthest remains 4. Since we are not at our current end yet, we keep moving. Wait, look at the code logic. We stop the loop before the last element because once we reach or pass the last index in our range, we are done. The dry run is complete. We reached the last index with a minimum of 2 jumps. Now that we have walked through the logic visually, let us see how these pointers translate into our Python code. We define our function jump, taking nums as input. We initialize our jumps, current, and farthest variables to 0. Then, we scan the array up to the second to last element. Inside the loop, we always update farthest by taking the maximum of itself and the reach from the current index, which is I plus nums of I. When our pointer I hits the current boundary, it means we have exhausted our current jump range. We increment jumps by 1 and set our new current to the farthest reach we have tracked. Finally, we return the total jumps taken. The time complexity is O of n because we pass through the array exactly once. The space complexity is O of 1 as we only use 3 integer variables regardless of the input size. This greedy pattern is highly efficient for range-based optimization problems. And that is the Jump Game 2 challenge mastered. Save this video for your next interview revision, and follow for more deep dive DSA explainers. Send this to your coding partner to help them level up.